Chapter 2 introduces stress and strain. These are terms that we use in everyday language to describe popular psychology. Someone might say they're under a lot of stress or under a lot of strain, as if they mean the same thing. The field of psychology took these words from the field of engineering mechanics, where they have very particular meanings. Let's consider a piece of metal that has a length L and a cross-sectional area A. If we pull on it with a force P, the stress is the force divided by the cross-sectional area that is perpendicular to the loading direction. In mathematics, another word for perpendicular is normal, so the stress we have is called a normal stress. The symbol for normal stress is lowercase Greek letter sigma, so sigma equals P over A. When we pull hard, the piece of metal will stretch. The change in length is lowercase Greek letter delta. The strain in the piece of metal is the change in length divided by the initial length. Units cancel, so strain is unitless. Sometimes you will see strain reported in percent. The symbol for strain is lowercase Greek letter epsilon. For example, let's look at a 2-foot-long bar of steel loaded in tension with a force of 45 pounds. It has a cross-sectional area of 0.3 square inches and it stretches 0.04 inches. Stress is P over A, which works out to 150 psi. Strain is delta over L, which works out to 0.0017. With most materials, you should end up with a decimal number with zeros. If you end up with a number bigger than 1, either the material is some sort of rubber compound, or you've made a mistake in the math or the unit conversions someplace. Let's try an experiment where we apply different loads to this steel bar and calculate the stress and the strain. Next, we'll plot the stress values versus the strain values on an XY plot. The data points seem to lie along a straight line. For example, let's say a steel wire has a tensile strain of 0.0006, and we want to know how much stress is in the wire. Starting with the definition of Young's modulus, we rewrite the equation algebraically to solve for stress. We can find the value of Young's modulus for steel in Appendix B. Plug in the numbers, then introduce a unit conversion to obtain a stress value of 124 megapascals. Now let's pull the steel wire even harder. At some point, the stress-strain curve stops being a straight line and starts curving over to the right. This transition occurs at the yield point of the material, where the stress level in the steel is called the yield strength. We keep pulling on the wire, and the curve arcs upwards to a high point which is called the tensile strength of the steel. It's also called the ultimate tensile strength. Then the curve starts to arc downward and it stops where the steel breaks. We call the first part of the curve, where it's a straight line, the elastic curve. In most of this course on strength of materials, we'll stay in the elastic zone. This is typically where most mechanical and structural components are actually used. The second part of the curve is called the plastic curve, where the metal undergoes plastic deformation. We're using the word plastic in its 19th century meaning. That is, a material that changes shape, kind of like soft clay. The reason we use the word plastic to describe polymers is because in the raw state, they are formable. Plastic deformation is important because it's how we actually make things. If you want to manufacture a paper clip out of a piece of wire, you have to deform it permanently by creating 3 U-shaped bends. To do this, you have to be between the yield strength and the tensile strength of the material as you bend the wire. If you want to use a paper clip, you want to stay below its yield strength so that the clip keeps the sheets of paper together. We can plug in the definitions of stress and strain into the Young's modulus equation and solve for deflection. Now we have a useful equation for finding the deflection if we know the load, length, cross-sectional area, and Young's modulus. Let's look at an example. A chandelier weighing 80 pounds hangs from a steel wire, and we want to know how much the wire stretches. The cross-sectional area of a round wire is pi over 4 times the diameter squared. The wire stretches 0.16 inches. So far, we've only looked at pulling and stretching, but we can also squeeze and compress mechanical and structural components. We need a sign convention to distinguish between pulling and pushing, so we say that tensile stresses are positive and compressive stresses are negative. If a solid is being stretched, we say that it has positive strain and deformation, and if it's being squeezed or compressed, we say it has negative strain and deformation. We defined normal stress, sigma, as a force divided by the perpendicular area that it acts on. There is another type of stress where the force is divided by a parallel area that it acts on. This is called shear stress, and it's still P over A. If we take 2 plates and glue them together, the shear stress in the glue is P over A. Here's an example of shear stress in a manufacturing operation. A flat punch blanks out 6-inch diameter circles out of sheet metal that is 30 thousandths of an inch thick. Shear stress is force divided by the area that it acts on. In this case, it's not the area of a circle. The punch is shearing a cylindrical surface equal to the circumference of the hole times the thickness of the sheet metal. The shear stress produced by a 4-ton press is 14,150 psi. If the shear strength of the sheet metal is larger than this number, then you can't make the part. If that's the case, then you have several options. You can use thinner sheet metal, weaker sheet metal, a higher capacity press, or a beveled punch that doesn't cut the metal all at the same time.